Once we have symbolized our complex sentence, we'll want to be able to construct a truth table for it. In order to do that, we need to take a minute and remember our rules for truth tables. So our negations, those are the ones that we read as not and symbolize with this tilde symbol. Are false if the original statement is true, true if the original statement is false. They're just the opposite of whatever we're looking at. Conjunctions, those are the ones that we read as and symbolize with this wedge symbol that points upward. Those are true if both of the statements we're combining are true. They're false otherwise. Disjunctions, those are the or statements. We symbolize those with the wedge shape pointing down. Those are false if both the original statements are false, and true the rest of the time. So as long as at least one of the original statements is true, the disjunction is true. Conditionals, those are the funky ones. That's the if-then that we symbolize with an arrow. That's false if the antecedent, that is the if part, is true, and the consequent, the then part, is false. It's true the rest of the time. So it's true whenever the if part is false. It's true whenever the then part is true. Our last connector was the biconditional. That was the if and only if, and we symbolized that with the double arrow. That's true when the original statements have the same value. It's false if they're different. Okay, let's use these and see how we compute the truth values in the columns of a truth table. So suppose we want to create a truth table for the statement, Alice has a cat, but not a dog. First, we identify the simple statements. Alice has a cat. We'll call that P. And, well, so Alice has, but not a dog. So not a dog, we want this to be positive. Alice has a dog will be our cue. Okay, how should we symbolize this? Well, the only conjunction in the Schoolhouse Rock sense, in the grammatical sense here, is but. That wasn't one of the words on our list. But we saw before, by looking at truth tables, that but is the same as an and. So this is actually going to be an and statement. And what? Well, Alice has a cat, that's before the and, so P. And not a dog. So Alice has not a dog. Alice does not have a dog. Not Q. That's our symbols for the statement. Okay, now we're going to make a truth table. We have two simple statements, so we'll need 2 to the second power equals 4 rows. Two simple statements, we need 4 rows. Remember, every time we add a simple statement, the number of rows we need doubles. Why is that? Well, our rightmost simple statement here, that's going to just alternate true, false, true, false. And then our P statement, our statement to the left here, we need 2 trues. So a true with each value of Q. And 2 falses. A false with each value of Q. Technically, our goal here is to get just every combination of truth values for P and Q, all 4 possible combinations. But if you lay them out in that way, it's easier to keep track of. So alternate in the rightmost column, and then 2, 2 in the column to the left of that. If you had a third column to the left of that, it would be 4 trues, 4 falses, and so on. We will see more of that later. Okay. Next, we want to set our truth table up to help us compute this. We'll need columns for every step so that we can show every step of our calculation here. The simplest part of our calculation is negating a simple statement. So looking at our big long statement here, we see that we have a not Q, but we don't see not P anywhere. So we'll have a not Q column. How do we compute that? Remember, negation has the opposite truth value of what's being negated. So not Q has the opposite truth value from Q. So when Q is true, not Q is false. Q is false, not Q is true. Q is true, not Q is false. Q is false, not Q is true. That's how we fill in that not Q column. In every row, it's the opposite of the truth value that we see for Q. Now that we've filled in a column for every negation of a simple statement we see, next we fill in a column for everything that is put together by combining two things we already have. In this example, all that's left is the whole statement. So all that's left is to make a column for P and not Q. How do we compute those truth values? Well, and is true only when the two things being anded together are both true. So here, P is true, not Q is false. They're not both true, so and is false. Here, P is true, not Q is true. Those are both true, so the result is true. Here, P is false, not Q is false. Those are not both true, so the result of and is false. Here, P is false, not Q is true. Those are not both true, so the result of and is false. Our final answer to this problem is this column. False, true, false, false. Coming up with that column was our goal. The not Q column, we developed that on the way as part of our work. I mention this because in some of the homework, you're just going to be asked to enter that final result column to save you from having to type all of this into the computer. So you need that not Q column in order to figure out the truth values for P and not Q. But the final answer just consists of that last column.